Hi friends, welcome back to our YouTube channel. Today we have to discuss about BCD Synchronous Down Counter or Mod 10 Synchronous Down Counter in Digital Electronics course, Digital Logic Design course and Switching Theory and Logic Design course. First of all, what is BCD? We already know that BCD stands for binary coded decimal. In BCD number system, total 10 digits are available that are 0 to 9. Every digit can be represented by using 4 bits. Next one, Mod 10 Synchronous Down Counter. We already know that mod n counter contains n number of states. In the same way, mod 10 counter contains 10 states starting from 0 state and ending with 9th state. Total 10 states are available. Now we have to counting starts with 9 and ending with 0 because it is a down counter. Now, to design BCD synchronous down counter or a mod 10 synchronous down counter, we have to use the 6 steps. The first step is determine how many number of flip-flops are required and decide which flip-flop we have to use. Okay. We know that in BCD, every digit can be represented by using 4 bits. To store 1 bit, we require only 1 flip-flop. To store 4 bits in BCD, we have to use 4 flip-flops. Okay. In BCD, every digit can be represented using 4 bits. To store 1 bit, we require 1 flip-flop. To store 4 bits, we require 4 flip-flops. So therefore, number of flip-flops required that can be denoted by small n, that is equal to 4. Okay, next. Once we are knowing the number of flip-flops required, next we have to know the possible number of states in BCD synchronous down counter. Number of possible states that can be denoted by capital N is equal to 2 power small n. We already know that small n value is equal to 4, that is equal to 2 power 4. So that implies 16 states. So starting with 0 and ending with 15. So total 16 states are available. Next one, maximum count value, so that is equal to n minus 1. So n value 16, so 16 minus 1, that is equal to 15. So maximum count value is 15 and the minimum count value is equal to 0. So 0 to 15, total 16 states are available. Next one, here we have to use JK or T flip-flop to design BCD synchronous down counter or mod 10 synchronous down counter, but here we have to use T flip-flop. So this is the first step. In the first step, we have to know about how many number of flip-flops are required to design BCD synchronous down counter. That can be denoted by small n, that is equal to 4. Next, we have to find out the possible number of states that are present in BCD synchronous down counter or mod 10 synchronous down counter. So that is equal to 16, that can be denoted by capital N, so that is equal to 16. So 0 to 15, total 16 states are possible and the maximum count value is equal to 15. Next one, we are using either JK flip-flop or T flip-flop to design BCD synchronous down counter, but here in this problem I am using T flip-flop to design BCD synchronous down counter or a mod 10 synchronous down counter. Next, step 2 is write the excitation table of decided flip-flop. Here the decided flip-flop is a T flip-flop. Now we have to write the excitation table of T flip-flop. In the excitation table, the present input, the present output and the next output. That means Qn is nothing but present state and Qn plus 1 is nothing but next state. That can be taken as inputs and T can be called as excitation input. Excitation input. Okay, here Qn and Qn plus 1 can be taken as inputs. So there are two inputs. With two inputs, how many number of possible combinations? We are getting 0, 0. So 0, 1, 1, 0, 1, 1. Now for each and every combination, we have to find the excitation input T value. T value is equal to 0 when the present state and the next state bits are same. If T value is equal to 1 when the present state and the next state bits are different. Here we are taking the first row. Here 0, 0. Both bits are same, then T value is equal to 0. Now consider the last case. Here 1, 1. Both bits are same, so that T value is equal to 0. Consider the second row and the third row. Both bits are different, then T value is equal to 1. This is the excitation table of T flip-flop. Next, in step 3, we have to draw the state diagram of BCD synchronous down counter or a mod 10 synchronous down counter. Okay, so here I am taking 10 states. Okay, out of 16 possible states, only 10 states are valid state and the remaining 6 states are invalid states. Okay, so in BCD, with each and every digit can be represented using 4 bits. With 4 bits, how many number of possible combinations we are getting? 16 possible combinations we are getting. Among the 16 possible combinations, first 10, that means 0 to 9 states are valid states and 10 to 15 are invalid states. So only valid states are present in the state diagram. Invalid states are not shown in the state diagram. Okay, so the valid states are 0 state, 1 state, 2 state, 3 state, 4 state, 5th state, 6th state, 7th state, 8th state and 9th state. Okay, so among the 16 possible states, the first 10 states are valid state. The next 6 states, that is 10 to 15, are invalid states. Next one, each and every state can be represented using 4 bits. So here this is 0, 0, 0, 0. Here this is 0, 0, 0, 1. Here 0, 0, 1, 0. 0, 0, 1, 1. 0, 1, 0, 0. 0, 1, 0, 1. 0, 1, 1, 0. 0, 1, 1, 1. 1, 0, 0, 0. 1, 0, 0, 1. Okay. So now it is a down counter starting with 0 state. Okay. Then it goes to 9th state. Then it can goes to 8th state. Then it can goes to 7th state. Then it can goes to 6th state. Then it can goes to 5th state. Then it can goes to 4th state. Then it can goes to 3rd state. Then it can goes to 2nd state. Then it can goes to 1st state. Then it can goes to 0 state. Okay, starting with this state and finally it can goes to again 0 states. So total 0 to 9, 10 states. 10 states are valid state. The remaining 6 states are invalid states that cannot be shown in the state diagram of BCD synchronous down counter. Because of only down counter, we are starting with 0 and goes to the maximum count value, that is 9 among the valid states. Okay, then each and every time the count value can be decremented by 1 and finally goes to the 0 state. This is the state diagram of BCD synchronous down counter. Here 0 to 9 are valid states and 10 to 15 are invalid states. Only valid states are present in the state diagram. Invalid states are not present in the state diagram. Next, we can go for step 4, that is write the circuit excitation table. Now, in the circuit excitation table, the first column represents the present state. The next column represents the next state. The next 4 column represents the excitation inputs. Okay, now each and every state contains 4 bits. Among the 4 bits, this MSB bit can be represented as Q1 and the LSB bit represented as Q4 and the middle 2 bits represents the Q2, Q3. Okay, so the 4 bits present in each and every state can be represented as present state bits, that are Q1, Q2, Q3, Q4. Q1 is the MSB and Q4 is the LSB. Next one, for Q1 state, the next state is Q1 plus. For Q2 state, the next state is Q2 plus. For Q3 state, the next state is Q3 plus. For Q4 state, the next state is Q4 plus. When the present state is Q1, Q2, Q3, Q4, the next state bits are Q1 plus, Q2 plus, Q3 plus, Q4 plus. Okay. Next one, for calculating T1, we are considering Q1 and Q1 plus as inputs. For calculating T2, Q2 and Q2 plus as inputs. For calculating T3, Q3 and Q3 plus can be considered as inputs. For calculating T4, Q4 and Q4 plus can be taken as inputs. Now, first, starting with the present state is 4 zeros. 0, 0, 0, 0. This is the present state. What is the next state for 0, 0, 0, 0 present state? The next state is 1, 0, 0, 1. 1, 0, 0, 1. Now, this can be taken as present state. When the present state is 1, 0, 0, 1, what is the next state? The next state is 1, 0, 0, 0. Now, this can be taken as present state. What is the next state? The next state is 0, 1, 1, 1. Now, this can be taken as present state. What is the next state? The next state is 0, 1, 1, 0. Now, this can be taken as present state. What is the next state? The next state is 0, 1, 0, 1. Now, this can be taken as present state. What is the next state? The next state is 0, 1, 0, 0. Now, this can be taken as present state. What is the next state? The next state is 0, 0, 1, 1. Now, this can be taken as present state. What is the next state? The next state is 0, 0, 1, 0. Now, this can be taken as present state. What is the next state? The next state is 0, 0, 0, 1. Now, this can be taken as present state. What is the next state? The next state is 0, 0, 0. Okay. Now, by observing this table, so this is the input. Okay. In the input, how many number of bits are there? Q1, Q2, Q3, Q4. That means n is equal to 4 number of bits in the present state. With 4 bits, how many number of possible combinations? So that is 2 power 4, that is 16 possible combinations. So among the 16 possible combinations, 0 to 9 are there. Okay. So here among the 16 possible combinations, 0 to 9 are valid states. That means first 10 states are valid states and the remaining 6 states, 10 are invalid states. That invalid states cannot be represented in the truth table also. That means, so 1, 0, 1, 0, 2, 1, 1, 1, 1 are invalid. Okay. Now, how to fill this T1, T2, T3, T4? For T1, we have to consider Q1 and Q1 plus as inputs. So, by using this excitation table, we have to fill T1, T2, T3, T4 excitation inputs. For T1, Q1 and Q1 plus as inputs. So 0, 1, both bits are different. T1 value is 1. here 1, both bits are same, T1 value is 0. Here 1, here 0, both bits are different, T1 value is 1. Here 0, both bits are same, T1 value is 0. Here 0, both bits are same, T1 value 0. Here 0, both bits are same, T1 value 0. Both the bits are same, T1 value is 0. Both bits are same, T1 value is 0. Both bits are same, T1 value is 0. Both bits are same, so T1 value is 0. Next, for filling T2 column, we have to consider Q2 and Q2 plus as inputs. Here 0, both bits are same, T2 value is 0. Here 0, both bits are same, T2 value is 0. Here 0, here 1, both bits are different, T2 value is 1. Here 1, both bits are same, T2 value is 0. Here 1, both bits are same, T2 value is 0. Here 1, both bits are same, T2 value is 0. Here 0, both bits are different, T2 value is 1. Here 0, both bits are same, T2 value is 0. Here 0, both bits are same, T2 value is 0. Here 0, both bits are same, T2 value is 0. Now, for filling out T3 column, we have to consider Q3 and Q3 plus as inputs. Here 0, both bits are same, T3 value 0. Here 0, both bits are same, T3 value 0. Here 0, 1, both bits are different, T3 value is 1. Here 1, both bits are same, T3 value 0. Here 0, both bits are different, T3 value is 1. Here 0, both bits are same, T3 value 0. Here 0, 1, both bits are different, T3 value is 1. Here 1, both bits are same, T3 value 0. Here 0, both bits are different, T3 value is 1. Here 0, both bits are same, T3 value is 0. Now, for filling out T4 column, we have to consider Q4 and Q4 plus as inputs. Here 0, 1, both bits are different, T4 value is 1. Here 0, both bits are different, T4 value is 1. Here 0, 1, both bits are different, T4 value is 1. Here 0, both bits are different, T4 value is 1. Here 0, 1, both bits are different, T4 value is 1. Here 0, both bits are different, T4 value is 1. Here 0, 1, both bits are different, T4 value is 1. Here 0, 1, both bits are different, T4 value is 1. Here 0, both bits are different, T4 value is 1. Here 0, both bits are different, here T4 value is 1. In this way, we have to fill T1, T2, T3, T4 columns by using the excitation table of T flip-flop. Next, we have to find out the simplified Boolean expression for T1, T2, T3, T4 using 4 variable Karnaugh map because it contains 4 bits. Therefore, we have to use 4 variable Karnaugh map. In step 5, we have to find out the simplified Boolean expression for T1, T2, T3, T4 excitation input. For finding out T1 simplified Boolean expression, we have to use this Karnaugh map. For finding simplified Boolean expression for T2, we have to use this Karnaugh map. For finding simplified Boolean expression for T3, we have to use this Karnaugh map. For finding simplified Boolean expression for T4, we have to use this Karnaugh map. First, observe the T1 Karnaugh map. Horizontal side, I am taking Q1, Q2 inputs, and vertical side, I am taking Q3, Q4 inputs. In the T1 column, identifying only ones. Here 1 is there, the corresponding input combination is 4 zeros. Here 0, 0, here 0, 0, we are placing 1. Here 1 is there, the corresponding input combination is 1, 0, 0, 0. Here 1, 0, here 0, 0, we are placing 1. Next one, Invalid states are 10 to 15. So 10, 11, 12, 13, 14, 15 can be represented as don't cares because they are invalid states in 4 Carnot maps. Now only 2 ones are there. So these 2 ones can be formed as a pair by folding the Carnot map in the middle from bottom to top. These 2 ones are adjacent. They can be formed as a pair. Okay. So for this pair, horizontal side 0 0 is there. So here 1 0 is there. So the first digit belongs to Q1, the second digit belongs to Q2. The first digits both are different, so that we have to ignore Q1. Next, in the second digit Q2, both bits are same, so they can be considered. Q2 value 0 means Q2 bar. In the column side, only 0 0 is there. The first 0 belongs to Q3, second 0 belongs to Q4. Both are zeros, then we have to write as Q3 bar, Q4 bar. This is column side, Q3 bar, Q4 bar. This is the horizontal side, so we are getting only Q2 bar. Next, for T2, we have to identify in T2 column and observe only once. Here 1 is there, the corresponding input combination is 8. Next, here 1 is there, the corresponding input combination is 4. Okay, and 10, 11, 12, 13, 14, 15 are don't cares. Okay, here this one and this don't care can be formed as a pair, and this one and this don't care can be formed as a pair by folding the Carnot map in the middle from right to left. Okay, these two can be formed as a pair. Okay, because only 2 ones are there, 2 ones are not adjacent. So this one and this don't care can be formed as a pair. For this pair, so column side 0 0 is there, therefore Q3 bar, Q4 bar I am writing. In the horizontal side, I am taking 0 1 1 1. So first digit belongs to Q1, both bits are different, we have to ignore them. Second digit belongs to 1 1, it belongs to Q2, only both bits are same, we have to consider Q2. So Q2, Q3 bar, Q4 bar for this pair. For this pair, horizontal side only 1 0 is there. So this one belongs to Q1, I am writing Q1. This 0 belongs to Q2, Q2 bar I am writing. And column side here 0 0 1 0 is there. First digit belongs to Q3, both bits are different, we have to ignore them. The second digit belongs to 0 0 belongs to Q4, both bits are same, we have to consider Q4 value 0 means Q4 bar. Okay, so this is the simplified expression for T2 we are getting. Next, for T3 Carnot map, we have to identify the T3 column and identifying only once. This one belongs to 1 0 0 0 combination. So 1 0 0 0 we are placing 1. This one corresponding to 0 1 1 0. So here 0 1, here 1 0 we are placing 1. This one belongs to 0 1 0 0. So here 0 1 0 0 we are placing 1. And this one belongs to 0 0 1 0. Here 0 0, here 1 0 we are placing 1. So this one, this don't care can be formed as a quad. For this quad, horizontal side all the bits are different, we have to ignore Q1 Q2. In the column side only 1 0 is there. This one belongs to Q3, so that Q3 I am writing. This 0 belongs to Q4, I am writing Q4 bar. Next one, so for this one is adjacent even though it is used. So this one and this one can be formed as a pair. For this pair, horizontal 0 1 is there, that is Q1 bar and Q2. And the column side 0 0 1 0 is there. The first digit is different, we have to ignore Q3, and second digit is same, we have to consider Q4. Q4 value 0 means Q4 bar I am getting. Next, for this pair, so already it is there, this can be taken as this one, Q1, Q2 bar, Q4 bar. Next, for T4 column, for T4 corner map, we have to identify in T4 column, it contains all ones, we are placing all ones, 10 ones are there. So here, any coordinate map filled with ones and don't guess, its value is 1. Top 8 ones can be formed as oct, and bottom 2 ones and 6 don't guess can be formed as oct. By combining these two octs, we are getting T4 is equal to 1. So these are the simplified expressions for T1, T2, T3, T4 excitation inputs. Next, we have to draw the logic diagram by using these expressions in step 6. And this is the logic diagram of BCD synchronous down counter. In the step 1, we already know that 4 T flip-flops are required to design BCD synchronous down counter. T flip-flop 1, T flip-flop 2, T flip-flop 3, T flip-flop 4. For first T flip-flop, input is T1 and the outputs are Q1, Q1 bar. For second T flip-flop, input is T2 and outputs are Q2 and Q2 bar. For the third T flip-flop, input is T3 and the outputs are Q3 and Q3 bar. For the fourth T flip-flop, input is T4 and the outputs are Q4 and Q4 bar. It is a synchronous counter. Because of that reason, the same clock pulse is applied to all the flip-flops at the same time. All the flip-flops are synchronized with the same clock pulse. Now it is a negative edge triggered clock pulse. So bubble with arrow mark represents the negative edge triggering. Next one, the final outputs are Q1, Q2, Q3, Q4, and Q1 can be taken as MSB bit and Q4 can be taken as LSB bits. So these are the Q1 output, Q2 output, Q3 output and Q4 output. Now first I am taking T4 is equal to 1. Consider the fourth T flip-flop. T4 value can be applied as 1. Next one. So T3 output, so Q3 into Q4 bar. So here I am taking Q4 bar can be separated. Then we are getting Q1 bar into Q2 plus Q1 into Q2 bar. That can be written as Q1 exclusive or Q2. So first I am taking Q3, Q4 bar. So here this is Q3 and this is Q4 bar line. Okay, so this is Q3 and this is Q4 bar line that can be applied to two input AND gate. We are getting Q3 and Q4 bar. Okay, next one is Q1 exclusive or Q2. Here I am taking Q1, here I am taking Q2. That can be applied to two input exclusive OR gate. Then we are getting Q1 exclusive or Q2. So here Q4 output I am taking here. So this is Q4 bar and this is Q1 exclusive or Q2 can be passed to two input AND gate. We are getting Q4 bar into Q1 exclusive or Q2. Okay. Next, this output can be passed as two input OR gate as one input and another input is Q3 and Q4 bar. Finally, we are getting as this is the output Q3 into Q4 bar plus Q4 bar into Q1 exclusive or Q2 that can be passed to T3 output. T3 input, sorry. Next one. Next, that is T2. T2 is equal to Q2 into Q3 bar into Q4 bar. Okay, so first one is Q2 bar into Q4 bar. So I am taking Q2 bar, I am taking Q4 bar. That can be applied to two input AND gate. We are getting Q2 bar into Q4 bar. This output and Q1 output can be sent to two input OR gate. Then we are getting Q1 into Q2 bar into Q4 bar. This is we are getting. Next one, this I am taking. So here this is Q3 bar line and this is Q4 bar line. So that can be applied to two input AND gate. We are getting Q3 bar and Q4 bar. This output can be sent it to two input AND gate as one input, and another input is I am taking Q2. Okay. So the output of this AND gate is Q2 into Q3 bar into Q4 bar. Okay, here this is one output and this is another output. These two outputs can be sent it to two input OR gate. Then the output is Q1 into Q2 bar into Q4 bar plus Q2 into Q3 bar into Q4 bar. That output can be sent it to T2 input. And the last one is T1 is equal to Q2 bar, Q3 bar, Q4 bar. So I am taking this is Q4 bar line and this is Q3 bar line and this is Q2 bar line. These three inputs can be sent to three input AND gate. So the output is Q2 bar, Q3 bar and Q4 bar. That can be sent to T1 input. So this is the logic diagram of BCD synchronous down counter or mod 10 synchronous down counter. So for constructing this logic diagram, it is somewhat critical. Please observe carefully. Okay. I hope all of you understanding this video. If you really understanding this video, please click on the like button and share this video to your friends and classmates. If you have any doubts, please put your doubts in the comment section. I will try to clarify your doubts. If you like this video, please subscribe my YouTube channel, Dippala Srinivasa Rao. For better understanding this entire course, go to this channel and go to the playlist called DLD or STLD or Digital Electronics course. It contains approximately more than 340 videos. For better understanding of this entire course, go to the channel and go to the playlist called DLD or STLD or Digital Electronics course. It contains approximately 350 videos.